Good morning, everyone. My name is Antoine Dedieu, and I'm a research scientist at Google DeepMind, and I'm very happy to present a recent work with my amazing colleagues on improving transformer world model for data-efficient reinforcement learning. So in this work, we focus on Crafter, which is a 2D version of Minecraft, and more specifically on a recent JAX4 implementation called CraftAx, which is extremely fast, so you can run 250,000 agent steps per second on a single GPU. And the question we ask ourselves is whether we can design a new state-of-the-art agent on CraftAx Classic, which only interact with the environment 1 in step, which is a standard. So first, we propose a very strong model-free RL agent. And for this, we start from the previous SOTA baseline, which is a stateless Impala CNN actor critic policy trained with PPU. And we improve over this baseline in 2 ways. So first, we give a memory to the policy by adding a GRU. And what we found to be important is for the hidden state to be low-dimensional, as this forces the policy to focus on relevant bits of the past. And second, we increase the model size. This plus hyperparameter tuning gave us a model-free RL agent that not only improves over the previous best model-free RL agent, but also over the previous best model-based RL agent, which is Dreamer v3. This is a good place to get started. So next, we propose, now that we have a good recipe for training a policy, we propose to jointly learn a world model, use it to generate imaginary rollout, and further train the policy in imagination. So we follow the IRIS recipe. We jointly train a VQVAE, which maps each image into 64 latent code, and a transformer world model, which takes as input a sequence of latent codes and action coming from the policy and generate future latent codes. Once we have the future latent code, the decoder maps that back to the pixel space, and then the policy network can predict the future action. So IRIS only trained the policy using imaginary rollouts, and when we follow this recipe, what we found to be surprising is that the model-based RL agent performed much worse than our previous best model-free RL agent. So in the rest of the talk, we propose 3 simple improvements to progressively convert this poor baseline into a state-of-the-art agent. So first, we realized that only training in imaginary rollout is pretty limiting, especially given that we have collected rollouts in the environment to train the world model. So we propose to train the policy using both real and imaginary data. And what we found to be important is to wait for the world model to be good enough before using it to generate imaginary rollouts and train the policy. And so this method, which we call Dyna with warmup, gave us a 12% performance gain. Our second improvement is more CraftAx specific. Each image in CraftAx is composed of 81 patches. So we propose to factorize the encoder and map each patch into a latent code. This guaranteed that the latent codes are semantically grounded and gave us a 15% gain. We also realized that as we jointly learn the VQVAE and the world model, the latent code keeps changing, so the transformer world model has a moving target. Instead, we propose a simple nearest neighbor tokenizer, which look at each patch and add its nearest neighbor in the current codebook. And if the neighbor is too far away, it just adds the patch to the codebook and never updates the kit again. This guarantees that the world model has a fixed target, which makes its training easier, and gave us a 6% gain. Our last approach comes from the observation that all the previous work generate all the latent code in one image, one by one, starting from the top left and going all the way to the bottom right. And instead, what we propose to do is we propose to generate all the tokens jointly, which allows the transformer world model to jointly reason about all the tokens of the next frame. And this is simply done by modifying the attention mask of the transformer and by modifying also the supervision signal. This method, which we call block stitch of forthing, gave us a 3% performance gain and 2x speed up. So when we combine all those pieces, we have a model-based RL agent which achieves for the first time superhuman reward on CraftAx Classic, significantly outperforming all the previous model-free RL agents and model-based RL agents. And we conducted some ablation study to make sure that if we remove each of the improvement, performance drops, and also that if we start using the world model to train imagination too early, performance collapse. But if we wait for too long, performance also drops. Finally, we propose some qualitative evaluation of the world model, and we show that our best agent has a world model that generates fewer map and inconsistencies or hallucinations that do not respect the game dynamics. And we additionally propose a metric to compare the world model, also showing that our best agent performed best on this metric. Thank you for your attention.